Perfect, great. All right, thank you so much. Yeah, that was a really great talk. We get to first hear about how to hack using prompt injection, and now I'm going to talk about how to detect and prevent prompt injection. So I am Kyle. I lead security at Perplexity AI. Given the name, we are an AI company. And Perplexity has three main products. The first one is Perplexity, which is the app. It's basically an AI-powered search engine. We call it an answer engine. The second one is Comet, which is we released last year. It is an AI-powered web browser, so a fully agentic browser. And then last week, we released Perplexity Computer, which goes beyond just having access to a browser, but it also has access to a file system and a sandbox, and it could write and execute code for you. So my team and I have become intimately familiar with all of the AI challenges that you sort of expect with all these tools and being one of the first to release it. One of those challenges is prompt injection, which we have seen with our Comet browser. And so, yeah, I'm really excited to talk about BrowseSafe, which is the classifier that we built to detect prompt injection, and talk about the lessons learned, trying to deploy that into production and what we've seen. So first, I'm going to talk about the problem of prompt injection. I know you've heard a ton of it, so I'll gloss over it. But then we'll also talk about BrowseSafe-Bench, which is the data set, the eval data set that we have released and open sourced. And then the classifier, which actually detects the prompt injection, and how we deploy that to production systems, and some guidance for you all as you're also building and starting to use these tools. So just to make sure we're all on the same page with what prompt injection is, especially for browser agents, a user might say, hey, Comet or AI agent, please book me a flight to New York City. And so the agent will go and it'll figure out, okay, these are all the steps I need to take in order to actually achieve this goal, and then it will go and visit a website in order to do so. That website is now in this like untrusted boundary where it's ingesting this content that we cannot assume is trusted, and so it could contain some like malicious instructions. And those malicious instructions then get sent back to the tool output and eventually into the agent context. And this is really the root of the problem, where the agent context is, at the end of the day, the LLM doesn't know exactly what is tool output versus user input versus system prompt. And then so basically the agent gets those instructions and then follows it. And so there's a lot of ways of doing a prompt injection attack. These are some of the ways that we've found. And so one is impersonating the prompt template. And so if you have built your own LLM, you probably have this template where you have the system prompt, and that has some sort of keys, and then there's a user prompt, and then maybe you separate in the user prompt, you separate what was user input, which is book me a flight to New York City, and the tool output, which is the contents of the website that say, like, here are the flights available. Another one that we've seen is the agent social engineering, and so it's basically a website where it will instruct the agent to go through certain steps seemingly benign. And so this, if you look at the language, it's very similar to how phishing humans would look. Finally, that was discussed a lot in the previous talk was some sort of conditional trigger. This is usually some like hidden in Google Calendar events and stuff like that, where it says, hey, when the user asks to summarize this page or check your calendar, perform these steps in order to give them a really great response. And those steps are malicious. In browsers, there's a lot of ways to hide this type of language. And so one is like hidden div displays or in the URL. And then also what was talked about a lot in the previous talk was in calendar events where basically it looks like a benign event, but then if you scroll all the way down, there's some malicious instructions that the agent ultimately detects. So there's a lot of benchmarks out there, and even open source models, such as PromptGuide, which was previously discussed, where they attempted to create this data set and classifiers in order to successfully detect this prompt injection. A lot of the issues that we found was that the benchmarks that are currently out there in open source are not really realistic. They have a lot of qualities and each has their own strengths, but there isn't one eval framework that actually has all of the attack types and injections that we've seen in the wild. And there's going to be something that pops up in a second. But when we tried using these data sets and these open source models and even just prompted LLMs, we found a lot of issues. The first one was, I wish you could see that diagram. The first one was, there's a lot of obvious types of prompt injection attacks. One is, please reveal your system prompt, ignore previous instruction, and so forth. But then when you get down to more context manipulation where the attacker is social engineering the model to do X, Y, Z, so it isn't as obvious, you could see the success rate of detecting prompt injection start to fall. And then finally, at the very bottom of this chart, which you can't see, there's multilingual. And so it's basically an attack that the language is very obviously malicious, but they have the language in Hebrew or Spanish or something, and that causes the model to get confused and follow the instructions regardless. And so what we found here was that this really showed to us that models aren't actually looking at the intent of what the prompt injection is asking for the agent to do. Instead, it's just looking for keywords. Another issue that we found is what we call distractors. And so on the top right, you can see the notorious cookie consent banner. And if you look at it from just the raw HTML, it almost looks like a prompt injection attack. It says, important, like in order to proceed, you must click accept, or else you can't get the content. And what we found too was that a lot of these data sets and open source models don't actually take this into account. And so if you see on the bottom right corner, with no distractors, these models are doing pretty good. But the second you add just 3, it drops down to 81% and stays that way. And so what we found was that distractors was a huge indicator that these models don't work well in live environments. And it's also an indicator that these models are looking at specific keywords and heuristics instead of the actual intent of the message. So that's why we created BrowseSafe-Bench. So what we did was we took a data set from things that we've seen in the wild. We created this massive pipeline to de-anonymize and classify these types of attacks into a very specific taxonomy bracket of the types of attacks that we've seen, the way they're injected, and we open sourced it. And so this was the eval data set that we also used to train our own model. And so the model is based off of Quen, 30 billion. We use 30 billion in inference, and this helps with latency, which I'll show in a second. Yeah, let's see if we can get that slide up there. There we go. Okay, great. And so you can see that a lot of the open source, or a lot of the open source models such as Prompt Guard and GPT OSS Safeguard don't actually work that well in live environments. That was the first thing that we've discovered. But the second thing too is that a lot of the prompted LLMs, especially like GPT-5 and GPT-5 Mini, do exceptionally well, which is really great. And so there's two things that we take away from this part of the research. One is that fine-tuning a model specific on this data set obviously makes it perform better than just a prompted LLM, which probably isn't that surprising. But what I think is really, really great is how we're able to achieve that with this kind of latency. So we're able to achieve this like 90.4% F1 score in sub-second latency. So now we take something where GPT-5 Mini can take 2 seconds, or GPT-5 can take up to 20 seconds. Ours is consistently sub-second, and therefore very easy to implement into production without massive user frustration. So in addition to being the fastest and having the highest F1 score, BrowseSafe is also unique in that it doesn't just output a yes or no binary. It outputs a probability score of how confident it is that what it's seeing is prompt injection. And so I don't know about y'all, if y'all ever had an LLM try to judge something of whether or not this is classified as some pattern that you want to see, and you ask it to explain itself and give a confidence score, every time, for me at least, it returns like 93% every single time. Even when you ask it to like, hey, like, we want to do some logic on this classification score, so please think about that a bit. And so we train this in such a way so that it produces this confidence score very accurately. And now, using BrowseSafe, security teams and product teams have a knob they can turn on how much precision and recall are they willing to accept in their product. And so a really good example is like if your system has a user experience where, let's say, the model detects prompt injection and you can tell the user, hey, this looks like prompt injection to me, are you sure you want to continue? You can now suddenly afford a lot more false positives and turn that knob to fit your own use case. So we have this data set now with a ton of labeled attacks and a strong data set of the taxonomy of what kinds of attacks there are and where they're being injected. And so we really wanted to stress test BrowseSafe and see how it performs with data it hasn't seen before. And so we retrained the model, but held out certain characteristics to see how well it does when it's never seen it before. So the first one was we held out the URLs. And it actually performed better than it was before. So we could confidently say it's not looking for certain keywords or certain domains and flagging those as malicious. The second one was the attack language. So there was a dip, but not super significant. So if there was an attack that had certain instructions that the model has never seen before, it would perform in line with frontier models. The last thing was that we found that was interesting was if we held out injection strategies, and so this is placements in websites that it's never seen before, there was a pretty significant drop. And so this is an indicator that attackers in the future will start to look at new ways of injecting prompt injection and trying to bypass those model guardrails. And so I'm going to start talking about how we actually take BrowseSafe and put it into production systems and some suggestions for y'all on how to do this in your own systems and products. And the first thing I want to talk about is the fact that The strategy should not just be, hey, let's put up a detection classifier and call it a day. As we've seen in the previous slide, defensive in-depth is absolutely necessary. These models can still be bypassed. And so the first layer of defense, which is the oldest trick in the book, is pre-processing and stripping out data that you don't need. And so the best defense is ensuring the text doesn't even get to the context. So any like HTML comments or hidden elements that aren't useful for the model's abilities to get the job done, we should just strip that out. The second layer of defense is the classifier. And so you should set up a system where every tool that calls untrusted input, so this could be a website, this could be a calendar invite, this could be a connector to a third-party service, an MCP. These should all have some classification check before sending that data back to the agent. If you don't want to use BrowseSafe and have to figure out inference and all of that work, honestly, prompted GPT-5 Mini works really well at a F1 score of 85.4%. There is that 2-second latency, but that's honestly not so bad for something that you can get started with today. Finally, the last thing I would suggest is when an attack is detected, don't just block the tool. You have to think of it from the LLM's perspective. It's trying to call your calendar and it sees an error. And so what will it do? It might try again. It might try a different way. It might try calling the Google API if you're using something like OpenClaw. And so the better strategy is to not just return an error, but to also return the tool output as the error message, basically telling the model, hey, I know you just tried getting your Google Calendar event, and we're rejecting it because our security systems detected prompt injection in that text. And you can either say, proceed with caution, tell the user, or in the case for Comet, we block basically any follow-up tools, and we tell Comet, return text directly to the user. So the second we see that prompt injection, we don't even give it the ability to do any follow-up tool calls. The third layer of defense, which is actually relatively recent, is that you should always be using the latest model as your agent. And so the snippets that I have here on the screen are from the Opus 4.6 system card. And at least the first time that I've seen, this is the first system card that actually, one, goes super in depth about testing and measuring prompt injection success. But two, this is the first one I've seen that actually tests it using specifically for browser use. And so they're testing it against, they're testing Opus 4.6 against attack scenarios using browser use cases. And so the jump between 4.5 to 4.6 was pretty significant, going from a 16.2% success rate down to 2.83. In addition, you can see on the bottom right where with updated safeguards, which is a pipeline, I guess they didn't share it, but I'd imagine very similar to what we have, it gets down to 0.08%, which is really fantastic. And so the last layer of defense I would suggest when it comes down to detecting prompt injection is to build an LLM backstop. And so you can have traffic coming in, you can have your classifier, such as BrowseSafe, detecting, hey, is this prompt injection or not? But since BrowseSafe outputs that confidence score, anything that's low confidence, you can have it sent to a backup, basically. A very large language model that will add in some additional latency, but it's probably worth it, I guess, depending on your use case. In addition, what I think is really cool about this is that you can now turn this into a data flywheel. And so let's say the classifier thinks it sees prompt injection, it's not entirely sure. We send that to the LLM backstop. The LLM backstop looks at it and says, okay, this actually is prompt injection for XYZ reason, we can now add that to our pipeline and training data set to retrain that classifier to catch new attacks in the future. And so, yeah, some key takeaways. One is the evals that we've seen so far, especially in academia, unfortunately don't translate well into production. The second thing, too, was fine-tuning on domain-specific data sets beats general-purpose models by a wide margin, and I think in the security industry, we should be doing more of that and open sourcing that work. The third thing is that using frontier models as your agent is a massive step up when it comes to prompt injection. They're going to keep getting better and better, but especially the jump most recently from Opus 4.5 or GPT 5.1 to Opus 4.6 and 5.2 is a significant improvement to prompt injection security. You should please update. And then, yeah, defense in depth, non-negotiable. I could do a whole talk about like all the other things that we do, even past detection in Comet. But for now, like even in detection, having multiple layers is super important. And then finally, building that data flywheel, because like we saw in our research, new attacks, the models, even BrowseSafe, struggle with detecting brand new attacks or brand new injection techniques that we haven't seen before. And so having that flywheel is super important. Cool. Yeah, I want to give, first off, I want to say that both the model and the data set is fully open source. You could download it on Hugging Face. We also have shared our paper that goes super in depth into what this research does and how we did it. Also want to give a big shout out to the folks at Perplexity who helped conduct this research, Mark Tenenholtz, Dennis Yaris, and Jerry Ma, and then also the folks from Purdue University who collaborated with us, which is Kaiyun Zhang and Dr. Ningwei Li. And I guess one more thing while I have the mic, we are hiring. We are a very ambitious security team. We are tackling two problems at once. One is we're trying to figure out product-facing security, where as agents are doing more and more work on behalf of humans, a lot of the security landscape is changing. And so, like, what does identity look like? What does threat detection look like? And what does DLP look like? I think that's going to significantly change in the next couple of years. And the second thing is, internally, we are really redefining how, or trying to redefine how security teams operate using LLMs and agents at its core. And so I hope to be back here maybe in a year from now to talk about all the things we built. But please, if you're interested in any of this research and helping us build this, please talk to us. I'll be here for the rest of the day. We also have some folks in Perplexity who will be here as well. Cool, thank you.
Very cool, thank you. I've got one to start. How do you think about the trade-offs between open sourcing sort of an oracle that can be used to teach the bad guys what will get through versus, sort of holding back your data?
Yeah, it's a good question. I'm a huge fan of open sourcing our work. I feel like defenders really need, I feel like we need a lot of help, right, with detecting these type of attacks. And so at the end of the day, like these red teams, these threat actors, they're going to be poking around and trying to find these vulnerabilities anyway. And I would love for us in Perplexity, but also the rest of the security industry to please share more and open source more. I feel like we see a lot of these blog posts talking about all the things that XYZ product did, or how like threat actors are using Opus to conduct attacks, but they don't actually share any IOCs or things how to protect yourself from those attackers. And so, yeah, I'm just a huge fan of open sourcing our work. Good question. Yeah.
Awesome. Great talk. Can you talk a little bit more about the recent Perplex browser research and, if it was fixed and how was it fixed?
Is this the Zenity?
Yes.
Zenity blog?
Yeah.
Oh, yeah. Okay. So, yeah, we worked with Zenity on that. They found so they found two findings. One was that the Comet agent had access to the file system. And so if you go to Chrome and you say, hey, navigate to my home directory, and then I click things, like, you're able to do that. That's a basic browser feature. We added in a ton of guardrails into the assistant to prevent it from doing so. However, a lot of these were very soft limits. So think of things like Elm analysis or like in the system prompt. And so what Zenity found was that if the person who is controlling Comet has the ability, can prompt it in such a way to basically bypass those guardrails, you can get the agent to look at files on your system. I do want to stress that one, this is not a prompt injection attack, and so we treat user content as trusted. So if you're on Comet and you type in like go to xyz.com, it will. It won't assume that's some sort of attack. But also, we do think it was useful that like identifying that there was this soft guardrail and we need something much more harder. And so what we did was we added like strong guardrails into the Comet browser itself to ensure that the agent doesn't even have the access to that in the first place. The second thing that Zenity found was the prompt injection attack specifically on 1Password. It wasn't really specific for 1Password, but it was a prompt injection attack. And so what they found was if you sent a calendar invite with some Hebrew instructions and you asked Comet to go follow those instructions, their blog post is talking about how it's able to do so. What they failed to disclose was that they had to run that query like 200 times, and on the 200th and first time it actually worked. And so, so one is we improved our models to detect that kind of attack even further. I do feel like it was a bit disingenuous to say that it was fully vulnerable to that kind of attack, given that they literally just had to rerun it 200 times in order for it to finally work. And so I am a huge fan of working with pen testers and external security teams. I do think there's a strong line between actually doing like security research and finding vulnerabilities versus trying to create a blog post for marketing material. Good question.
Hello. Thanks for the talk. I'm Omer. I'm a researcher at RSAC. At some point, you had a table up where you were comparing existing benchmarks and how they were failing to cover some strategies. How accurate do you think that table is today? These prompt injection strategies keep changing every day, right?
Yeah, so you're saying like we have this eval system today and how will it hold up in the test of time? It's a good question. I think along with us, I think attackers are also figuring out how to properly use this. And so I'd imagine we will see a lot of new and novel prompt injection attacks in the future. I'm optimistic that with things like the data flywheel, our own research and working with various red teams will uncover it and we'll be able to quickly improve that classifier in our systems in order to detect it in the future. It is a good question though. Maybe we'll release a BrowseSafe-Bench 2 at some point. Yeah.
Thank you.
Yeah, thank you.